we have here another problem, and this is an example of a continuous beam, and we are going to determine the moment at B using moment distribution method. The first step in the analysis of moment distribution method is, first we have to assume that all supports are fixed. So we have here three supports. We have support A, support B, and support C. We will assume these supports are locked or fixed. Then we will compute the fixed end moments. Since our beam is loaded a concentrated load with a different position, we will find the formula for a concentrated load. So from the fixed end formula, we have this formula. So you can find this formula for any from a strength of materials book or from a theory of structures book. So we have this formula for a concentrated load. Okay, so we will compute the fixed end moment of each support. But before computing the fixed end of each support, we have to divide it into segment. So we have here segment AB and segment BC. So now we have, for segment AB, okay, we have here, okay, we will use this formula. Okay, this one, and this is the formula for our fixed end moment. So we have here fixed end AB, that is equal to, so for the first concentrated load, okay, we have negative 20 times 3 times 6, okay, times 6 squared. Okay, 6 squared. Okay, divided by the whole span for segment AB is equal to 9, and this is also in squared. Okay, then you have another concentrated load, so we have negative 20, but here the A is already 6 meters and the B is also equal to 3. Okay, so you have 3 squared all over divided by, okay, 9 squared. So we will compute. Okay, we will compute. So you have 20 times 3 times 6 squared, okay, divided by 9 squared, okay, plus we also have negative 20 times 6 times 3 squared divided by 81. So that is negative 40. So the unit is kilonewton meter. For the fixed end moment of segment BA, okay, we have this formula. We have positive BA squared times B over L squared. So we have positive, okay, we have positive 20 times 3 squared times 6 divided by 9 squared plus 20 times 6 squared times 3 divided by 9 squared. So the result is equal to positive 40 kilonewton meter. Okay. For the segment B to C, we have a concentrated load at midspan. That is loaded at midspan. So we will use this formula. And for the fixed end moment, we have negative PL over 8. Okay, so for the fixed end moment of B to C, we have negative PL over 8. So P is 60, the concentrated load is 60, length is 8. So we have 60 times 8 divided by 8. So the answer is negative 60 kilonewton meter. Then for the fixed end moment of C to B, that is equal to positive 60 times 8 over 8. So this is positive 60 kilonewton meter. So we have now computed the fixed end moment. For the beam stiffness, we have two formulas. We can use absolute K, which is equal to 4EI over L. And we also have relative K, which is equal to I over L. That is for constant modulus of elasticity if your beam having the same material. But in this problem, we can still use the absolute K, which is equal to 4EI over L. So EI here is constant. So what matters for each segment is the length of the beam. So for this beam stiffness, for the span AB or for the segment AB, we have 4 EI over 9. And for beam BC, we also have 4 EI over 8. Then, after getting the beam stiffness, we will determine the distribution factor or the DF. So this is the ratio of the bending stiffness of the member to the sum of the bending stiffness of all the members connected to the joint. So looking back to our beam, so all members are connected to the joint B. So we can determine that distribution factor for this. And for the distribution factor for the hinge support and for the roller support, we have equal to 1. So for the fixed end, there's no distribution factor for the fixed end. So for our beam, the support are hinge and roller. So the distribution factor for this, for DFA, so we have distribution factor. So for the distribution factor for AB is equal to 1. Okay, and for CB, distribution factor for CB, that is also equal to 1. Okay, so for the distribution factor for segment B to A, we have the formula or the ratio of the beam stiffness of AB divided by the sum of the members, or the sum of the bending stiffness of all the members connected to joint B. So that is KAB plus KBC. Okay, so we have 4AI divided by 9. Okay, you have 4AI divided by 9 plus 4AI divided by 8. So we will compute. So you can cancel there the EI because for the entire span, the EI is constant. So you have 4 over 9, okay, divided by 4 over 9 plus 4 over 8. Okay, that is 8 over 17. 8 over 17. Then for the distribution factor for BC, you have K BC divided by K AB plus K BC. So still we have here 4 EI divided by 8 divided by 4 EI over 9 plus 4 EI over 8. So what is the answer? We will compute. Okay, so 4 over 8 divided by 4 over 9 plus 4 over 8. So that is 9 over 17. Okay, so we have here the distribution factors for each segment. Then, next, we will tabulate our data in order for us to understand fully the method of distribution, or for the moment distribution methods. And now we will tabulate our results. So we have here our support. So we have support A, support B, and for support C. So this is your support A, your support B, and for your support C. Then for the distribution factor, for support A, we have 1.0. And for C, we also have 1.0. For the distribution factor for B to A, we have 8 over 17, and BC is 9 over 17. So we have 9 over 17. Okay, so we have this one. Then our fixed end moment. Okay, for the fixed end moment of A to B, we have negative 40. Then we have for B to A, we have positive 40. So we have here negative 40. Then you have positive 40. Then for BC, we have negative 60, and CB, positive 60. Okay, you have negative 60, then you have positive 60. And now, we will unlock each support, then distribute the unbalanced moment at each one or the adjacent joint also. So we will unlock the support A, then support B, and support C. Then we will distribute the unbalanced moment for this by using the distribution factor. So for our support A, we have, okay, you have positive 1, positive 40. So we will balance, we will balance the moment at each support. Then for the support B, the moment for B to A, that is positive 40, and for the moment for B to C, that is negative 60. So there is an unbalanced moment for this. So we have to balance, and we have for positive 40 minus 60. So there is a discrepancy of positive 20. Then we will distribute it using distribution factor. So you have positive 20 times 8 divided by 17. So that is 9.442. So we will use at least 3 decimal places. So we also have positive 20 times 9 divided by 17. So we have 10.588. Then we will check if the moment at B becomes 0. So we have 40 plus 9.412 plus 10.588. So that is already equal to positive 60 minus 60. So that is equal to 0. For support C, you have distribution of factor of 1.0. So positive 60 times 1. So to make it 0, so we have negative 60. Okay, so this is now for our first distribution. So this will be our first distribution. Then after our first distribution, we will carry over 1/2 of the moment with the same sign to the other end of each span. So okay, so here for the 40, we will distribute this, or we will carry over 1/2 of 40 to other span or to B, A. So we have, this is positive 20 having the same sign. Okay, so then for this one, we also have to carry over 1/2 of this to the other span. So that is 9.412 divided by 2. That is equal to 4.7, okay, 4.706. Okay, the sign is positive. Then you have 10.588 divided by 2. So that is 5.24. So that is also, okay, positive 5.294. Then for the 60, that is negative 30, 1/2 of 60. Okay, so this is our second distribution carryover. So we have here carryover, second distribution. Okay, carryover, second distribution. Okay, this is your second distribution. Then we will repeat the process. We have to balance we will use the distribution factor to balance the moment of each support. So we have here, this one is equal to 4.706 times 1, that is 4.706. That will be now negative. So negative 4.706. Okay, so here we have positive 20 for another, for B to A, and for the span BC you have a moment of negative 30. So this is an unbalanced moment of positive 10. So we will distribute this positive 10 by using the distribution factor. So we have 8. So 10 times 8 divided by 17. So that is equal to positive 4.706. Then 10 times 9 divided by 17. Okay, that is 5.924. Positive 5.294 rather, 9294. Okay, so then we have here negative 5.294 because 5.294 times 1, okay, is equal to 5.294. Then we will change the sign to make it 0 for the support C. Okay, so we will check for joint B if the moment there is already balanced. So we have 20, positive 20 plus 4.706 plus 5.294. So you have 30. Okay, so minus 30, that is equal to 0. So here the moment of each support will be 0. So again, we will, after distribution, we will carry over 1/2 of the moment with the same sign to the other end. So other end or other support or to each span. So we have here, okay, you have 40. You have negative, okay, you have 40.7, oh no, 4.706 divided by 2. So that is equal to 2.353. So negative 2.353. So here you have positive. So you have positive, okay, positive 2.353. Okay, positive 2.353. Then here you also have 5.294 divided by 2. So you have 2.647. Okay, that is positive. And here you have negative 2.647. Okay, so this is our moment for the for our support, and we need to balance again. Okay, we need to balance again for the moment of each support using distribution factor. So we have negative, okay, negative 2.353. Here you have positive 2.6, no, sorry, negative 2.647. Okay, so for joint B, we need to balance again. There is an unbalance moment. So we have 2.353, okay, minus 2.647. So to balance this, to balance this, so that, because all are negative, so to balance this, we will put this positive, okay, 2.353, then this is also 2.647. So everything will become 0. So again, this line here is my third, no? This is the carryover of the for the third distribution. Okay. So now I guess I have to stop here, because if you observe, the value here will always repeating if we continue the distribution or the carryover until it became negligible. So for this problem, I need to stop here. I will not continue my carryover for the fourth distribution, because as what I've said, for the third distribution, the value there keeps on repeating. Only the sign is changing. So now I have to sum all the moment. So I need to get the summation of all the moment of support A, B, and C. But for some problems, you need to keep on repeating all the steps until the carryover moment becomes 0 or negligibly small. But there are some problems that we can get the answer up to fourth distribution. You have to check the values. If you find it that it is already okay, if the value is already okay to stop, so you have to stop. So now I have to stop until third distribution only. So we need to summation to sum up all the values. So for the support A, so negative 40 plus 4.706 minus 4.706 plus 2.353 minus 2.353. So that is equal to 0. We know that the pin or hinge support don't have a moment. So the moment there is equal to 0. For the ruler also, the moment is also equal to 0. So we have to check. We have positive 60 minus 60 plus 5.294 minus 5.294 plus 2.647 minus 2.647. That is also equal to 0. So for B, we know that B have a moment. So we will add plus 40. So we have positive 40 plus 9.412 plus 20 plus 4.706 minus 2.353 plus 2.353. Okay, so that the answer is 74 point. Okay, that is positive 74.118. Okay, for the right side of B, so we have here negative 60, okay, negative 60 plus 10.588 minus 30 plus 5.294 minus 2.647 plus 2.647. Okay, it should be balanced. So the answer is 74.118. Okay. A, that is balance. So you see, the moment at B is already balanced, and that is equal to 0. Now, you need to have a decision what will be the moment of B, because you have there the moment of B for the left side, and you also have for segment AB, and you also have the moment for the right side of B for the segment BC. So if you are, because since in our problem, for our problem, we are asked to determine the moment at B. So you have to give me the final answer of your B. You cannot say that the moment is positive 74.118 or negative 74.118. So you need to give the value of the moment of B. Since we assume that the clockwise moment is positive and the counterclockwise moment is negative, and for our fixed end moment, we have this one. For the fixed end moment AB, we have negative, and for the fixed end moment BA, we also have positive. So this is our assumption that the moment AB is counterclockwise direction, so that is negative, and for the fixed end moment BA, that is clockwise direction, and that is positive. So for the final value of our moment at B, we will take the moment the right side of B. So now you can say that therefore the moment at B is equal to negative 74.118 kilonewton meter. Now you are ready. Since you already have the moment at B, you can get the reaction of A, reaction B, and reaction C. But since for our problem, we are going only to determine the moment at B, so we will stop until here. So therefore, the moment at B is equal to negative 74.118 kilonewton meter. Thank you, and I hope you understand.